Hello, everyone, and welcome to lecture one of the lecture on atomic spectroscopy. So this is module three. We're going to do foundations of atomic spectroscopy. So here we're going to learn and contrast the differences between atomic and molecular spectra. We're going to learn to apply the quantum mechanical model to predict the origin of these spectra, define resonance lines, distinguish the three modes of atomic spectroscopy, describe the atomization sequence, apply the Beer-Lambert law to atomic absorption, and also to select an appropriate atomic technique for a given analytical scenario. So today we'll work through these various sections. So just to remind ourselves, in module two, we covered molecular spectroscopy. So that was UV-Vis, FTIR, Raman, and we were looking at the spectra of intact molecules or ions in solution. And so this meant that the absorption occurred over relatively broad wavelength bands. The limitations that we can address are that these molecular spectroscopies identify functional groups and chromophores, but they don't tell us exactly which elements are present. And so for heavy metal surveillance, nutritional analysis, and so on, we need to know which elements are present. And so this is our atomic spectroscopy. But of course, we have to get to these atoms somehow. So for example, in our lead nitrate solutions, this would be the molecular or ionic form. In water, we have to atomize these and turn them into individual free atoms in the gas phase. So the process by which that occurs differs depending on the techniques that we're using. But once we have those free atoms, then we can apply spectroscopy to those and we can quantify them. So the key insight here is that every element has a unique set of spectral lines, which is their atomic fingerprint. Measuring those lines gives elemental identity and concentration simultaneously. So this leads us into the different types of spectra. So we have continuous band and line spectra. So continuous spectra are going to be emitted by hot solids and blackbody radiation and so on. And they give us sometimes a continuous background. Molecular band spectra are what we've been seeing in module two, and those are looking at broad bands which are relatively close together. And they're common in UV-Vis, and they are also seen in some parts of FTIR, like, for example, the OH stretches. Now, the one that we're concerned with in atomic spectroscopy is the line spectrum. These are the atomic line spectra. So these produce discrete sharp lines, which are precisely defined at specific wavelengths, which are going to be indicative of the different atoms that we're dealing with. And so these are the reason why we have these individual lines is because in atoms we only have electronic transitions. There are no vibrations or rotations because there are no bonds. So the basis for this is that that we just have that electronic absorption. So we have a quantized system, and so the absorptions or the emissions are from one electronic state to another. And so the electrons occupy discrete energy states, and only specific quantized energies are therefore allowed. And so the ground state down here, E0, is the lowest energy, most stable, and these excited states are accessible through photon absorption or thermal collision to get to higher energies. And so a photon will only be absorbed if the energy which is given to the atom precisely matches that which is required to bridge that gap, okay? And so, of course, we can cast our minds back to module 1 and 2, where we learned about Planck's relationship, and we can see that the wavelength that is required is equal to hc over delta E. And so the selection rules, of course, limit which transitions are allowed, so which ones will be sharp, which ones will be strong, and so on. And so each element emits or absorbs a unique set of sharp lines, and this is a characteristic atomic spectrum, since there can only, if we have a specific set of lines, then we can only have that kind of transition. So the resonance lines, which are our analytical standard, so this is going to be the line which we utilize primarily to identify the different elements. And so what is a resonance line? It's the transition from the ground state to the first excited state. And so we know that at room temperature, almost all of the atoms are going to be in the ground state. If we call back to the Boltzmann distribution at 2,500 Kelvin for sodium, we see that the ratio between the excited and ground state is 10 to the minus 4. So a very, very small percentage of atoms are in the excited state at that temperature. Therefore, the transition has the highest absorbent population. Since that is what we're going to be looking for, that is what we will use. So nearly all atomic absorption analyses use this ground to first excited state transition. Alternative lines can also be used to avoid spectral interferences, for example, but in general, we utilize that ground to first transition, so first excited state. So why do we use this and why is it in the UV? So the large energy gap between the ground and first excited states typically corresponds to that UV. Over here on the right-hand side here, we can see the different regions that some of the elements have. So many of the elements will be in the UV, but some will be in the visible and some will be in the infrared. Those are usually the ones that we've, for example, are familiar with from our flame tests, like the calcium, sodium, and so on. And so this is because they have relatively low ionization potentials and their energy gaps are quite a lot lower in energy. So the three analytical modes that we're particularly interested in are absorption, emission, and fluorescence. So absorption is the absorption from the ground to the excited state. So that's going to be usually for our resonance lines would be the ground to the first excited state. So that absorption has a wavelength associated with it. And in this case, we're doing the same thing as we do with UV vis. We are, for molecular spectroscopy here, we are also measuring the input intensity versus the output intensity to see which wavelengths have been absorbed and to what extent, okay? So for this, we need an external light source. So usually that's going to be our hollow cathode lamp, which we'll learn about in lecture 2. And so the signal here is that there's a decrease in transmitted intensity. We have one element per lamp, and this is the most common technique. So it's very easy to run, and so it's quite common. Emission then is the second one, so that's also common, primarily because of its ability to be multi-element. So in this case, we don't need an external source. The heating from the plasma, which is an integral part of ICP, that is sufficient to create an excited state population. Then whenever those relax down to the ground state, they emit different wavelengths of light, which again correspond to different elements. And so therefore we can see which elements are present. The last one then combines both absorption and emission. That's fluorescence, so it's a stimulated emission. So in this case, we have some sort of a light source which will be used to excite a ground to excited state population, which will then emit light as it relaxes down to the ground. But this is ultimately a less common technique, primarily used for very low concentrations. Okay, so why is atomization essential? So the problem here is that real samples contain analytes as ions or bounded molecules. In the case of ionic and molecular species, they produce molecular or no atomic spectra. So they must be broken down first into free gaseous ground state atoms, and this requires progressively higher energy. So we're going to need energy to desolvate, we're going to need energy to volatilize, we're going to need energy to decompose, and we're going to need energy to atomize. So the atomization sequence, so the solution to aerosol droplets, dry salt patches are particles, then gaseous molecules, then free atoms. But we need to be careful at this stage. These free atoms are the analytical window that we're looking for. If we excite with too much energy, we'll overexcite and we'll create an ionic population, which will reduce our signal during that absorption process because the ions will have different energy level gaps. And so we want to avoid that, okay? So this efficiency of the ability to create these free atoms is the determining factor for our sensitivity. So we have three principal atomization sources. So those principal sources are the flame, the electrothermal graphite furnace, and the inductively coupled plasma. So in this case, we have a number of different options. Usually for atomic absorption spectroscopy, we will be using flame or the graphite furnace. So typically it's the flame, but the problem with the flame is that we need to use only liquid samples. The liquids must be totally homogeneous, and we need actually quite large volumes in order to measure. And as well as that, the temperatures reached are not particularly high, can reach around about 2,900 Kelvin with certain mixtures. So during this flame atomic absorption process, we need mixtures of a fuel and an oxidant. So the oxidant can be air, it can be N2O, and then the fuel is typically acetylene, okay? So this air-acetylene mixture is typically useful for most elements, and the N2O acetylene mixture is used for refractories. So we need to ensure that we have high temperatures in order to try and improve the efficiency so that we can try and atomize as much as possible. In the case of the electrothermal graphite furnace, that can be utilized for liquid samples. Much lower volumes are required because you're placing it sort of inside the oven and we don't need a continuous flow. But we'll see the inner workings of those systems shortly. Then from that, we can also use solids because I mean, if you're placing a little drop of liquid inside the oven, then you can also place a solid there, okay, which is something you cannot do with the flame system, which requires a liquid. Then the last one is not used for the absorption techniques per se, but it is used for the emission techniques and a closely related technique, which is the coupling of the inductively coupled plasma with mass spectroscopy, which we will cover in more detail in the mass spec module. But for now, we will focus on ICP OES. So this is inductively coupled plasma optical emission spectroscopy. So this has the advantage of being very, very high temperature because of its use of an argon plasma coil as a argon plasma, sorry, as a heating source. And then this generates a lot of free atoms. The issue is that you tend to get a little bit of ionization as well. It's an emission-based technique, so we're going to see and detect via the light which is emitted from the sample. The advantage here is that we're able to screen a lot of elements at the same time because any element or atom that is present will emit light, so we can measure that all together. So the general rule that we have is that the higher the temperature, we get a better atomization efficiency, which improves our sensitivity. But this also tends to lead to more ionization, which can be problematic for atomic absorption spectroscopy. So, of course, the Beer-Lambert law can also be applied to atomic absorption. Since it is an absorption technique, it's still the Beer-Lambert law covers the a relationship between concentration and the absorption. It's a little bit different from the way that it worked in UV-Vis, and that's primarily because of the nature of the instrument. So in the case of UV-Vis, we had a cuvette, in which we kept the sample in. Here, we keep the sample in the flame effectively, which means that we no longer have epsilon B, but epsilon B rather becomes a constant which is governed by the sort of system itself and the instrument. It needs to be prepared empirically from a set of standards. So looking at the overview of those atomic spectroscopy techniques, we have our atomic absorption spectroscopy, which is relatively low cost, but does require significant sort of quantities of material. For the flame, for the graphite furnace, we reduce that a little bit. They're both not multi-element, but they also don't have particularly low limits of detection in the flame. The graphite furnace improves that slightly down to nanograms per liter, but it doesn't ever really reach the sort of low limits of atomic fluorescence or an ICP-MS. Atomic fluorescence, as I said, is relatively esoteric, but in cases where you have very, very low concentrations and you need partial multi-element capacity, atomic fluorescence spectroscopy is still useful. ICP is the gold standard in terms of emission, primarily because it's got a very low limit of detection and is multi-element. Unfortunately, it is relatively expensive in terms of atomic spectroscopy. So let's have a look at our first worked example, which is the determination of the resonance line energy in sodium. So the problem here is that the sodium line has a ground state to first excited state resonance line at 589.0 nanometers. We want to calculate the frequency, we want to calculate the molar transition energy in kilojoules per mole, and we want to explain why this transition appears yellow in a flame test and why it falls outside the typical atomic absorption spectroscopy UV working range. We're given these constants. And why this matters analytically. So the energy of the transition determines exactly which hollow cathode lamp is needed and why all a sodium AAS work with a dedicated sodium lamp. Okay. So the solution here is given. So we calculate the frequency as being the speed of light over the wavelength. And so we get the frequency as 5.091 times 10 to the 14 hertz. We find the energy per photon, and by taking this relationship between the frequency and Planck's constant, we find out that the energy gap there is 3.373 times 10 to the 19 joules per photon. Of course, we want to know that in moles, so we calculate that by using Avogadro's constant. And so we see the interpretation that this sits in the yellow-orange visible region. Okay, the second worked example is the absorbance transmittance intercept. So a flame atomic absorption spectroscopy measurement for copper at 324.7 nanometers gives an absorbance of 0.415. Okay, so what is the percent transmittance? And if the hollow cathode lamp delivers an intensity of 8.5 times 10 to the 5 photon counts per second, what is the transmitted intensity? And then a second copper sample gives a transmittance percentage of 45.0%. What is the absorbance? So we got to remember that the key relationships here are that the absorbance is equal to 2 minus log percentage T. So we were given percentage T already. We also have absorbance, so we can rearrange that, and we can see the percentage T is equal to 10 to the power of 2 minus the absorbance, since we were given the absorbance already. That means for part A, we'll just have to use that equation. So percentage T is equal to 10 to the power of 2 minus 0.415, which gives us a transmittance of 38.5%. Then we want to know the transmitted intensity. So we know that it's 38.5%, which is 0.385 as a ratio. So then we see that the intensity is equal to the initial intensity times percentage T over 100. So the initial intensity here times the percentage, which was transmitted, gives us this much. So then we find out that the constant that were transmitted is seen as so. Then the last part, part C, is the absorbance from percentage T. So we know percentage T was 45%. So that's going to be A is equal to 2 minus log of 45. At 0.0 is equal to the absorbance being 0.347. Okay, so then we continue on and we have our case study, which we often have. So this is looking at technique selection for a nickel laterite mining facility. So the Mines and Geosciences Bureau commissions elemental analysis of 150 soil samples per batch from a nickel laterite exploration area in Surigao del Norte. Okay, so the target elements are going to be nickel, cobalt, chromium, iron, manganese, aluminium, magnesium, calcium, and silicon. So 9 elements with some refractory oxides, notably aluminium and silicon there. So we will have to acid digest our ores in order to make sure everything is in solution. Then we will have a relatively high iron background simply because of the relatively high concentration of iron in the ore. So we need to document it well, and we need to also justify the costs. So we do a cross-analysis table. We'll see that we have a number of criteria. We need to run 9 elements per run. We don't know exactly how many samples we'll be getting, but we assume that we will receive 150 per day. That means we're going to have a relatively high throughput. We're going to need a relatively high throughput. We know that we have a high iron matrix problem. Silicon determination is also an issue. Aluminium determination is also an issue because we have those targeted elements. So we need to analyze those. It's not a case of we can just leave it behind. Then we need to also consider the capital costs. Okay. Now the issue here is that flame atomic absorption spectroscopy, while useful for many of those elements, will not allow us to properly analyze aluminium or silicon, which means that we're going to need to do what? We're going to need to switch over to our ICP OES. And that has a number of other advantages. We can analyze all of the elements at the same time. We can manage our interferences. We're able to run all of those samples in one day, more or less. We can actually determine silicon. We can actually determine aluminium. We do, of course, have the higher cost involved, but ultimately, if we really want to analyze all of those things, we're going to have to bite the bullet and actually pay for it. So the ICP OES is the correct choice. A flame atomic absorption spectroscopy instrument would just be too slow of a throughput. I mean, even if we only measured 7 out of the 9 elements, It would still take far too long. We'd be spending weeks and weeks and weeks measuring these samples, whereas the ICP OAS would just give us the results much faster. Okay, so that was the end of lecture one, relatively short foundations. I mean, most of the foundations are taken from the foundations we had in module two. There's not really a huge amount of difference. Things that applied in module two's fundamentals often will apply in module three as well. So atomic versus molecular spectroscopy. So of course, molecular, we're looking at broad bands, intact analytes, identifies functional groups. You usually get your sample back at the end. Atomic, you don't get your sample back at the end, but you do have very discrete lines, very element-specific fingerprints. It does, however, require atomization first. You have a quantum basis then for this. So like, for example, the electrons occupy discrete levels. The transitions emit one wavelength at a time, and we will typically use our resonance lines. We, of course, have to understand the atomization, which we'll go into in more detail in lecture two. And of course, we have to remember that the Beer-Lambert law still applies in atomic absorption spectroscopy since it is still an absorption technique. Okay, so some practice problems for you to have a go at, and the solutions will be posted, are given here. So please have a go at those before they're posted. Even if you just have a thought exercise as to what are my steps here, what would I do? Okay, so coming up next time, we'll be looking at the instrumentation, we'll be looking at some of the atomization processes and some of the light sources. Okay, so if that questions are welcome to leave in the comments below. Thank you for listening.